In this lesson, we're again going to look at Ampere's law for the long straight wire again, but now we're going to have a much more realistic situation for the wire. The current is still coming out of the page for us, but now we're being told that the current density, the amps per meter squared, that current density is not uniform. And in wires, it typically is not uniform because the electrons repel each other. You'll get a higher current density at the outer radius of the wire as you get closer to capital R, and that's what this equation is saying. So the current density increases, in this case linearly with R, and since we know the current density has units of amps per meter squared, we immediately know that this constant beta, so that's not a B field, that's a constant beta, must have units of amps per meter cubed because R has units of meters, and one of the meters here will cancel out with the meters cubed on the bottom, and our units are consistent. Well, again, we're going to start outside the wire because outside the wire we have the current is all of it, and I'm not going to go through this derivation again. I just showed the three steps we take to get our result. The long straight wire, mu naught I, 2 pi r. When we are outside the wire, regardless of the current density configuration inside the wire, we will get our 1 on r, mu naught I, on 2 pi r that we normally get. Now, if we're inside the wire, now it's a little different. So I have it highlighted here, so please make sure you get this down in your notes. When we do Ampere's law inside the wire now, our Amperian loop doesn't change, so our basic analysis doesn't change. We have our Amperian loop runs counterclockwise inside the wire. The current's coming out of the page, so the B field is going to run counterclockwise as well. By symmetry, there's no reason to expect the B field should be different anywhere on the Amperian loop. The B field comes out, so our left-hand side of the equation really remains the same in all of these calculations. So we get B equals 2 pi r on the left-hand side. Now, the I enclosed is handled differently when we have an equation. So anytime, and this is important, anytime you are given the current density as a function of R and it equals any equation, right? Doesn't have to be linear, any equation. You have to use the calculus version of density. So density is current per area, but now it's the calculus differential I divided by the differential area. The differential area for the wire is always going to be 2 pi r dr. Wires are always cylinders, so we'll always have the full angular extent, 2 pi r dr for our differential area. Just memorize that. So when we solve it for di, we bring the 2 pi r dr up with the beta r, and we're going to integrate from 0 to I enclosed to get I enclosed, 0 to little r. Now that little r is the little r that goes to ds. So little r goes to ds. So that corresponds to our enclosed current. And we had beta r squared now because we have r and r here, r squared when it goes up. So the integral of r squared is r cubed on 3. So we have our I enclosed gets substituted in here, which is now shown here. And now we're done. We just have our algebra, our very nice calculation is done. We lose the 2, we lose the pi, we lose one of the r's. We get an r squared dependence from 0 to capital R. And the only thing we have left to do to complete our calculation here is to look at the intersection point and make sure that they coincide. When little r equals capital R, we have mu naught I on 2 pi r. When little r equals capital R here, capital R squared, we get this equation. And what you want to keep in mind now is we have to be consistent at this intersection point So now we know what beta has to be. We solve for beta, so beta has to equal the 3/2 I over pi r cubed, and that is often, almost always, a part of this type of question if it's asked as a quiz or a test question. So again, let me erase all my extra little checks and dashes here so you can see all of the annotations clearly. Pause the video if you need to copy them down at this point. And we're getting there, so hopefully Ampere's law is becoming more comfortable for you.